Okay, well, my computer says it's 7:30 here. Shall we get started? Hello, everyone. I'm Jan Rush. I'm VP of the DVAA. Harold asked me to lead the meeting tonight because he's not able to get internet access wherever he is in the world. So welcome, everybody. I know we're all really anxious to get to Michelle's talk. We have just a few business things to do first. So I'm going to share my screen, hopefully. Oops, that's the beat. So for those of you who are saying, hey, we're really wanting to go somewhere, we have a poll for, can you see my screen? Yes. We have a poll for you on going back to Radnor. So we'd like your opinion on that. Jeremy, you want to take over?
Yeah, so I'll introduce it a little bit. So we were hoping to get back to in-person meetings last fall, just as the COVID surge hit us. So hopefully this time we're finally out of it. So we're thinking about returning to meetings at Radnor. And I think it might be a little bit different because we're hoping to continue doing live streaming of the meetings even once we're there. Now, I can't guarantee anything just yet because we actually have to get into the building to test out the internet connectivity and all of that. But we're hoping to have live streaming of the meetings available as well once we return to in person. What we want to do right now is sort of gauge the temperature of the membership of, are we ready to return to meetings? Now, I suspect it's a little late at this point for March, but we were thinking about starting up in April. So let me see if I can lay out the poll here. No, that's not it.
Do I need to stop sharing?
No, I don't think you need to.
Okay.
Here we go. That should be there. All right, so the options we put here was return to in-person meetings as soon as possible, probably April, or continue with remote meetings at the time being. And if you're watching on YouTube, you can type your preference into the comments there, and I'll collate those as well.
Do we have some music, Jeremy, too?
Anybody do the Jeopardy music?
Yeah, I'll help.
Actually, what we can do is we can move on and we can just wait a little bit for the results to come in.
Right. I can't figure out where here where I do full screen. Where is that?
Go to slideshow on the top.
Top. Oh, okay, right.
And from beginning. There you go.
Okay. Alrighty. So, exciting thing is that observing feast season is almost here, and I hope you like my humor here. Just wanted to remind everyone of what's coming up. Right now, obviously, we're in the middle of the Winter Imaging Challenge, and Lou will mention more about that, I'm sure, when he gets the floor later on. We have our first public start party on March 12th, so hopefully we'll have good weather for that. We have a couple of outreach events in March. One of them is a star party at Anderson Farm Park. And then I wanted to remind everybody about NEAF, which, if you haven't been there, the Northeast Astronomy Forum and Space Expo is really a lot of fun. It's going to be live this year, at least the last I've seen, and they have lots of equipment on display, but also great talks. And it's you can go as a day trip. You can stay overnight if you want, but it's up in New York, and it can be a day trip. So check it out. And all the links you need are on the website. If you go to the event that's showing on your screen. So because I have the floor, I also wanted to mention something that's coming up in July, and we've agreed to help out with this. Exactly what we'll be doing is going to be up to discussion. We do have some time to plan it. But basically, this is run by the regional Rotary clubs, and it's called the STEM Youth Explorer Academy. It's going to be a camp at Albright College in Reading, PA. Lasts kind of over a long weekend. It's for 100 middle school students who have completed 7th grade, and they're all from underserved neighborhoods, people who have been recommended by their school, and they'll be on full scholarship from the Rotary. So during the day, they're going to be studying a curriculum that's developed by the SETI Institute. It's basically using Search for Life on Mars as an in to talk about a lot of things related to biology and chemistry, and to interest the kids in these kind of things. DVAA has agreed, along with some other regional clubs, to help them with what they call the Star Watch sessions, which are in the evenings, Saturday and Sunday evening. Peter Detterline, the former director of Boyertown Planetarium, is doing the planning of it, and there'll be members of other area astronomy clubs. So for us, I think the tough thing is the drive. It's not obviously that easy, or that it'll be challenging to get there and drive home at night. But I think it'll be a great chance to do something that's going to be really impactful for these 100 kids, and also to meet other people in the nearby astronomy community. So I just wanted to introduce it tonight. You'll be hearing a lot more about it later on, and I'll be happy to answer some questions after the meeting when we have our informal chat. Okay, now we've got some committee reports. I'm going to start with Brian.
Okay, we have 3 new members this month. Jesse Warchowski, Steve Hayes, and Lisa Gaines. And as of about 6:15 this evening, we have 222 members. That's all I've got.
Okie doke. Lewis.
Well, unfortunately, that number is slightly wrong. It's 174 members who are not required, but we have the 49 people who have not re-upped or still within the grace period for renewing. So I was going to hope to ask you all to please re-up if you've not re-upped for this year. Your dollars help us with our events and with completing our mission. Super simple. Go to the website, log in. It will guide you through the process of re-upping. And if for any reason you can't figure out how to log in, there is a support button, a support menu item in the upper right-hand corner of the website. Click on that. It'll give you information to call a real live human support person. So thank you very much.
Okay. Thanks, Lewis. I don't think I saw Roy on. Are you there, Roy? No. So I did mention the upcoming outreach on at Anderson Farm Park. I believe we have enough people for that, but if anyone would like to volunteer in addition, the person leading it is Al Lamperti, so you can get in touch with him directly.
Jan,
Mm-hmm.
where's that located?
Good question.
It's in Collegeville. Collegeville.
Okay, thank you.
Okay, now I'm going to turn it over to Lou for a astrophotography announcement.
All right, hello everybody. So what we've been doing recently, the past couple of months, about a handful of us have gotten together and organized an astrophotography group. We're ready to get started with live workshops, and we're planning on having them once a month, open to anybody who wants to participate. Our first workshop is going to be next in March, the Wednesday prior to the meeting. So it'll be March, I think that's 16th. If you want to show up, I'll post the link on the member section of the astrophotography page, which is something also new that we just built on the website. And in a minute, Scott's going to take you through that and give you a little tour. But one thing I I wanted to mention before that, we were asked by our wonderful club here to have a night of astrophotography for our April meeting, which is going to be our member month. So if you want to participate, this is open to anyone or everyone. It doesn't matter from beginner to advanced. If you want to participate, send an email to astrophotography@dvaa.org and it'll post on the forum. You don't have to put any of your images. Just let me know your name and about how many images you have you want to participate with. What's going to happen, I think it looks like our meeting might be live at Radnor. And if that's the case, I would just ask whoever is preparing images to prepare them on a PowerPoint or some kind of preferably PowerPoint presentation, or if you don't have PowerPoint, some other kind of format, so that we can put everything on a USB drive, especially if you can't make it and you want your stuff presented. But it'd be easier if we do it live, rather than having musical chairs of 15 or 20 people tripping over each other. So again, if you want to participate, send an email to astrophotography@dvaa.org or just post directly on the forum. And Scott will take you through, if he's here, there he is. Scott will take you through the new part of the website we just built and changes we've made. Hopefully it's enough to get anybody's interest. You are a little bit excited about astrophotography. We have a lot of resources, and there's definitely a lot of depth in the club. There's a lot of people here available to help you. So don't be afraid. If you would just, all you need is a DSLR camera. Doesn't have to be anything fancy. In fact, the one I use was obsolete more than a decade ago. So just don't think if you have a crappy camera, you won't be able to do this. You will. All you need, where there's a will, there's a way, and we'll help you. All right, Scott, take it away, bud.
All right. So as Lou said, we just got kind of a group together started for the astrophotography stuff. So on the DVAA website, there's a imaging page. So under imaging resources, it brings you here. Currently, the main thing is the astrophotography challenge. We're doing a winter challenge with it. That was in the newsletter. So all the information is in the newsletter, as well as on the website here with it. So, all the information's here, and then there's a link for submitting your images for the challenge there with it. And then at the end of the winter contest, all the submissions get rated in the documents folder with it. And then the winner gets their information put on the website and in the newsletter with it. So, the upper section, the upper section kind of covers, any new news information with it. And then on the website, there's more information. There's a link to our astrophotography forum with it, slideshow of various different images from various people for, astrophotography type of thing with it. So it's a nice slideshow to see a lot of the different potential that people have with it. Some of the winter upcoming events and things with it. And then there's a useful link section, and then a further down resource section. And this is a section that we're still working on to collect more information as it. There's a lot of information, obviously, for getting started in astrophotography and even more complex things with it. So we're looking at how to use the website to really centralize all the information for people, so that way they have a good idea of it. And then as we do the astrophotography workshops that Lou mentions, be able to put links to those with it. Hopefully those get recorded and put on YouTube and things with it. And then there's a list of some of the astrophotography members that we have that are in the group together that can specialize and be able to answer any questions or anything you have regarding astrophotography. So I think I covered everything. Did I miss anything, Lou?
I don't think so. I mean, do you want to click on the folder and show people what they need to do to upload their images?
Yeah. So so for the winter challenge, If you click on this link with it, it takes you to the documents folder. So, I mean, you can actually go to the documents folder and traverse it. But under astrophotography for the contest, right now there's only the winter challenge. Obviously, there'll be other challenges of it. But for your image, just upload your image with it. The title of the image with it, the description. In the on the astrophotography page, there's a list of kind of what information to put in the description of it, because we want to make sure that we capture relevant information for what the picture is, the exposure, the equipment used with it, but all that information, there's a link on the astrophotography page for it. And then, put your name as the author with it, the date, and then hit select to actually upload your image with it. And then once the images are uploaded, unfortunately, with the website, you can't view the image with it. You can only download an image and then be able to look at it. But there is a rating that you can go in and look at other people's images and rate them. And that's what we're looking for everybody to do is, as a group, be able to rate other people's images. And then, the image with the best rating will be the one that we have. But there's several different categories we have for it that's listed on the main page. But here's a good example of information. So what telescope, the reducer, what mount was used, and then the exposure links that were used and everything with it. So good information on what the image is, so you get a good idea of the picture. And I mean, I can show you everyone real quick what it, I guess this is Harry's picture with it real quick of one that he uploaded with it. So just an image of the M42 and Running Man Nebula. So okay.
Thank you very much, Scott. I guess the winner also we will feature in our member meeting in April. So you're going to get exposure twice. Once in March when you win the contest, and again in April. Hey, look at the incentive to join.
So is that a pun?
I don't know. Don't confuse me, Lewis.
Not hard to do.
No, it's not.
Is that everything, Lou?
I think so, yeah.
It's a lot. Thank you so much for all that this group has been doing. It's just been really fun to see this blossom in the last couple of months. And there are something like, I'm not sure what the number is now, but last time I looked, over 80 people that are members of the club that indicated they were interested in astrophotography, something like that. So we know you're out there. Get involved in the Winter Challenge and join the group.
Jan, I got to give you credit. Thanks for lighting a fire under my butt. Otherwise, probably still wouldn't be doing anything, but thank you.
Okay, well, you do all the work. Okay, I guess, Jeremy, we're ready for the poll results, right?
All right, here we go. Let me see if I can share these on screen. So here we go. This is actually a reversal from the last time we did this, when the overwhelming majority was in favor of not returning to in-person. So maybe we are finally getting to the other side of that mountain. So there were a number of responses on YouTube, and we have actually 21 people watching over there. A lot of the responses there saying, looking forward to return in-person meetings, but also very much want to continue live stream of meetings. And a lot of people on YouTube also said continue the live streams. But I'm not sure that was exclusive to having the in-person meetings. So we'll definitely want to do that. So I guess first step is I will reach out to Radnor, and I'm going to find out what the availability of the room is. It's obviously up to them whether they want to grant us access. But last fall, they seem to be up for that. And I know they are doing in-person meetings for the township. So I'm assuming that will happen. I guess we'll still have to decide about masks and things like that. I'm sure, between now and April, that's like 5 years in COVID time. So we'll be in touch, closer to the date as to exactly what the requirements will be. So I think that will be the way we'll go from there. So I will contact Radnor and find out what their requirements are. Also, as far as the live streaming of meetings go, we do have a programs technical committee. So Scott Vanneman and Lou Berman have joined me on that, because running the remote meetings is not going to be a one-man show. It's a little more complicated than doing it here. If anyone else would like to join in, if anyone else would like to help out with running the Zoom and running the YouTube and maybe running the we're gonna have to do a live test at some point. We're gonna have to go to the Radnor building probably sometime in March to test everything out, make sure the internet connection works, make sure that audio levels are acceptable and so on. So if anyone wants to help out with that, just send me a message in the chat and you will get added to the program's technical committee. So we have 3 on it so far, but I wouldn't mind having another 1 or 2 people who would be willing to help out. All right, any questions about meetings? Maybe I can pull this down.
Going to tell us about next month?
Yeah, all right, yeah, Brian said he's willing to help, so I will add you. All right, so in March, we're gonna have John Conrad, who is a several time speaker to us, always given great presentations on a number of topics. And in March, it'll actually be a 2-part presentation. It'll be March 18 and 25. And his presentation is going to be on getting to space and operating in space. So I think that's something that a lot of us have become interested in, watching the web launch and learning about different types of orbits and how we get out to that distance and how can we track web on the way out there. So I think that'll be a really interesting presentation. And that's actually what John did for a living. You know, everything else that we've heard from him has been kind of his vocation on the side, his interests in other topics. But this is what he actually did for his career. So I think that'll be interesting to hear that. And in April, as you just heard, Lou and his friends will be doing a astrophotography member night. So hopefully, and that hopefully will be our first in-person meeting. In fact, our first in-person live streamed meeting. So that will be interesting. All right. So without further ado, let's get to this evening's main presentation. This is something we've been waiting a while for. We have Dr. Michelle Thaler, who is the Assistant Director for Science Communication at the NASA Goddard Space Flight Center. You've probably seen her before. She's a frequent contributor to a number of different television programs. She's been on the History Channel, the Science Channel, the Discovery Channel. She does a column for the Christian Science Monitor. She's done a number of TED Talks, done a number of videos for Big Think. And if you watched any of the James Webb pre-launch and post-launch events, she was one of the point people for that. So let's see, Michelle did her undergraduate work at Harvard and then did a PhD at Georgia State University in astrophysics, working on binary star systems and the life and death of massive stars. She did postdoctoral work at Caltech and has been a staff scientist and a manager of the Education and Public Outreach Program for the Spitzer Space Telescope, which was NASA's great infrared platform. In her research, she's used Hubble, the International Ultraviolet Explorer, ROSAT, and other telescopes. And today, or tonight, I should say, Michelle is here to share a very interesting topic that I think should be of interest to all of us, creating and maintaining a life-friendly planet. So this is something we've been waiting for a while. We wanted to get her here in December, actually right before the original web launch date, but that unfortunately fell through. But now we've got her back in February, so we're really happy. So please join me in welcoming Dr. Michelle Thaler.
Well, thank you. Yes, I had to keep changing because the web launch date kept changing. And so it was like, oh, I'm not going to be available that day, not that day, but finally it's up. So we know that we know that I can start giving talks and having a regular schedule. So yeah, let me share my screen and we can start to talk a bit about the topic tonight. So hold on a sec. All right. So, okay, if I share that screen there, can you guys see my slides? Is that
Yes.
Can you see me too?
Yes.
Yep.
Okay, cool. Yay. All right. This is actually becoming a really interesting discussion in science right now about, what makes a planet habitable. And there are so many factors we've never really considered. And now we're right up on the cusp of being able to tell whether some of the exoplanets in the night sky that you can at least point to the star and say, does that star have a habitable planet? There have been some really, really interesting results in the last couple of months about some of the planets in our own solar system and some possible life signs that we were not expecting. And then, it's amazing. I actually took this screen grab literally while you guys were talking in your sort of beginning of the meeting, because this changes every day. And this is a wonderful website called exoplanets.nasa.gov. And you can go there to find out all about the latest discoveries of exoplanets, how to find an exoplanet, different techniques, different missions. But one of the things that I really love is that they have a counter that changes all the time. And the counter, so as of today, we have 4,933 confirmed exoplanets. So that's how many we know for sure are there. And we're following up on about another 8,500 right now. Following up, so in order to really say that something is an exoplanet, you need to see it come around 3 times. Because if you're looking at a star and you're just studying the brightness of the star, the way we find most exoplanets is by seeing them transit across the star, making a tiny little eclipse, and then the light level from the star goes down, and you know that that's a planet. And there are plenty of other things that can affect the light levels of stars. I mean, a classic one is sunspots, star spots. So it could be that there's a really nice big sunspot going across the star, and there's really no way to tell that from a planet. What you need to do is get this regular drop in brightness. It comes back again and again and again in a predictable way. And so, people often say, what are the most common types of planets and the common types, what sort of stars have planets and all of that. We're still in the era of that being a very strong, what we call selection effect. When you think about something like the planet Jupiter, right? I mean, Jupiter is in an approximately 12-year orbit around the sun. The very first exoplanet ever discovered was about 25 years ago. So, there hasn't been time for Jupiter to come around twice. So you couldn't discover any planets out that far. And by the time you get to something like Saturn, Uranus, and Neptune, you could be waiting 100 years before you'd actually see that planet come around. So right now, we know of a lot of planets very close to their star. That's not a coincidence. Those are the ones we found because they go back and forth very quickly. And so, as this search goes on year to year to year, we expect to find thousands of new planets each year. And that's an amazing era of discovery to be in. So that's just, just stay tuned. Things will change as soon as they're written down, basically. Do you guys see that little red thing, that little red squiggle on your screen?
Yes.
What is that? I don't know what that is. Is it something on my slides? Hold on a sec. It's something here on my screen. Boy, I tell you, that's a new one. I've never seen that one before.
You've used the drawing tool to write
Yeah,
inadvertently.
but I didn't mean to. That's right. So how do I delete that?
Usually escape.
Okay.
That's weird.
It's one of those nights. I'm just going to stop sharing and see if I can do that again. Hold on a second. Let's share screen. Go back. All right. There we go. That should be fine. I'll try not to draw anything. All right. Anyway, so now we're up with the Webb Space Telescope. And as you mentioned, we just launched this thing. To give you an idea of the size of the mirror, here you have a comparison of the Hubble mirror with an astronomer. It's about 2.4 meters. And then this 18 segmented Webb mirror, about 6.5 meters in diameter. And of course, the greater the diameter, the better clarity we're going to get, the fainter objects we'll get. The Webb mirrors are coated with gold because that's very, very reflective in the infrared. And so as you know, the Webb is entirely infrared. Being a postdoc on the Spitzer mission prepared me well to talk about Webb. We will be seeing amazing images, but then of course we have the challenge of telling the public that yes, the images are real, but in order for your eye to see them, we'll have to assign false colors to the different wavelengths of infrared. And infrared has tremendous advantages when it comes to space telescope observing, because of course for things like exoplanets, you can get radiation from objects that are not hot enough to glow in visible light. So anything with a good thermal signal you can see. And then with the cosmic redshift, the farther out you look, the more reddened light becomes as it gets stretched out by the expansion of the universe. And so the Webb telescope really does have the capability to be able to see farther away than Hubble too. And we are hoping to see all the way back to what is known as the cosmic dark ages. And I don't know if you're familiar with that term. I bet a lot of you are. But there was a transition time roundabout, it wasn't a single wall. This is a bit uneven throughout the sky, but round about 500 million years after the Big Bang, there was a time when the universe went from being full of neutral hydrogen between the stars and galaxies, and neutral hydrogen is very good at absorbing light, to actually the hydrogen being ionized. And we think that happened when the very first black holes turned on, and these giant jets coming from the black hole disks, basically just strafed the universe and knocked all the electrons off the atoms in the interstellar medium and in the gas between the stars and galaxies. And so that's the time. I mean, basically as far back as you can easily see with a telescope is what we're going for. And now, as you know, it's actually in orbit. The thing that's amazing to us all is that everything works. And this is an animation, of course, a beautiful flyby of the Webb telescope. The astronomers, of course, they get really nervous when you portray it with light shining on the primary mirror, because no bright light should ever shine on the primary mirror. The mirror is pointed out into the darkness of space. And if either light from the moon or the sun or the earth ever hit that mirror, it would burn out the instruments. So it permanently looks away from the earth, the moon, and the sun. We will be able to observe all of the planets in our solar system farther away than the earth. So Mars on out, we can see. We will be looking for things like Kuiper Belt objects, very small distant objects. If indeed there is a hidden large planet out there, which there may be, the Webb will probably be involved in searches for that too. So, it's an amazing new observatory. There were 317 single point failures, little actuators that had to fire to get that thing to unfold, all of the different layers of the heat shield, the secondary mirror coming out, the primary mirror snapping into place. All 317 of them worked. And yes, if one of them would have failed, we wouldn't have been able to open it, at least not perfectly. There might have been some things that we could have saved. If not all the primary mirror had unfolded, we could have at least used part of the primary mirror. But things like the heat shield and the secondary mirror had to work. And amazingly, it did. So it's there. That was one of the most intense and active times in my career. So I'm kind of glad it's done, but it was also amazing. So here's an animation of that orbit. So, Earth is tracking around the sun, and then the Lagrange point, L2, is immediately opposite the Earth and the sun. It's about a million miles away from Earth. It's a stable point where the centripetal force and gravity balance out between the sun, the Earth, and the moon. And as you see here, I'll play that again just so you get a chance to look at that. It's kind of a nice animation. The idea is that the Webb telescope will always have its heat shield pointing in towards the Earth and the sun. And the wonderful sensitive observatory will be actually always pointing outward from that. So we do see the entire sky as we circle around in the course of a year. The telescope does have a little bit of pitch and yaw, but not much. We want to be very, very careful not to point anything towards the sun. So that's how the observatory will be flying in its configuration from now on. Okay, so this is something that I hope you will enjoy. So there are 18 segments. Each segment is able to operate independently. It has actuators that can move in many directions, forward, backward, up, down, pitch it, yaw it, all of that. And the adjustments have to be made to better than the wavelength of light that we're observing. And so, I've heard that say that's about, a thousandth the thickness of a human hair or better. And that's the accuracy that these particular telescope mirrors can be adjusted to. That in itself, I think, is kind of mind-blowing. This is a real image taken earlier today of every single mirror actually throughputting starlight onto it. So every mirror is now focused enough that starlight is falling on the mirror. And of course, what you're not seeing is a perfect point yet, because that's what we're going to be doing for the next few months. We're going to be doing very, very fine adjustments to go from what we call a point spread function, right? So there's basically some kind of a weird geometric pattern or blur that the light is coming through the detectors now. And each segment in turn will be adjusted carefully so that goes down to a single point. And when that happens, the telescope will be in focus. But the good news is every single mirror segment is now receiving starlight. At least we've done the rough adjustments, and now we go down to make those points smaller and smaller to get it all the way in focus. At this point, the telescope is largely usable, because one thing we've gotten very good at is taking out point spread functions electronically if we have to. So, as long as we know what the error is, we can usually take it out. But this is just the beginning. This is just the very rough adjustment. We think this is fabulous. This is working really, really well. And so, from now on, it's getting those all down to a single point, and then we'll start mission operations. Light is going through the instruments. So, that is a wonderful thing. I mean, the observatory, we're still fine tuning it, but it is working. Okay, so let's get to our discussion about habitability. Now, there are a lot of possibilities as to how life may form in the universe. And we only have an example of one, what happened here on Earth. I often get asked, can you make life out of anything besides water and carbon, the stuff that we're mainly made of? And the answer is, of course, that's possible. But one thing we know is that, carbon is very, very commonly made in the universe. Dying stars of many different masses and temperatures output carbon as they die. This is the cloud around, it's part of what we call the Carina Nebula in the Southern Hemisphere. And for those of you that know Eta Carina, one of the, I guess technically the most luminous star. It's not the brightest star because Sirius is closer, but Eta Carina, and I hope I'm not drawing, but if I point here, there's Eta Carina, which is a giant binary system. These two stars are probably somewhere between 50 and 70 times the mass of the sun. It's one of the stars that we're looking for to possibly blow up violently, fingers crossed. It could become something that we call a gamma ray burst, which is actually powerful enough that if we're sort of right along the jet that comes out of a gamma ray burst, this would be close enough to destroy the Earth. But we're hoping that the chances of that are relatively small. So gamma ray bursts do go off in jets, and we'd have to have pretty bad luck to be right down the barrel of the jet. But that's one we're looking at. There's several in the sky that if they actually do go gamma ray bursts, it's enough to worry a little bit about. In 2005, by the way, I don't know if you know this, a significant part of our atmosphere was blown away by a very energetic event about 50,000 light years away in the galaxy. A neutron star had a tiny little quake on it. Just a little quake, and it released enough energy to blow off the top of our atmosphere 50,000 light years away. So, one of the reasons we talk about this is what is our environment and space like? But this nebula, all of that beautiful dark dust you see, a lot of that is carbon. The universe makes carbon, the chemistry that makes us up, carbon-based molecules, organic molecules. It's very, very common. And carbon has this wonderful capability of wanting to form bonds. It's actually just following the second law of thermodynamics, just letting entropy play itself out. Carbon wants to drop down into lower energy states by sharing electrons with other atoms. And so carbon is a sticky atom. It wants to form bigger, more complex molecules. And then you combine that with water and the idea that water is a wonderful solvent. Things can dissolve and form more complex structures. And it has this property that almost no other liquid has. And that is that when you freeze water, ice floats. For most things in the universe, when they go from a liquid to a solid state, they actually get heavier and they would sink. And this wonderful property of water, it protects life. That when things freeze on the surface, the bottom oceans are protected, as opposed to the ice just sinking and letting the water on top get colder and colder and colder until everything's in ice. And this is one of the reasons why even the outer moons of our solar system, like Europa and Enceladus, moons of Jupiter and Saturn, they have these wonderful protective shells of ice. And so these are two of the reasons why we love looking for carbon in water. It's not that life couldn't possibly use anything else, but these are great things to build life. Now, this is an artist's conception of a young solar system. And I'm going to compare this to some actual data that we have, but this sort of shows you what I'm going to talk about. Interestingly enough, one of the problems about where the Earth formed close to the sun billions of years ago is that we don't find a lot of water or carbon in the inner solar system. We now can actually survey other young solar systems forming. And what we find is that very close to the young star, and young stars often are kind of violent. They give off very violent flares. There's very strong winds of particles that come off these young stars. The young stars tend to blow lighter material out into the outer parts of the solar system until finally the temperature is cool enough that these they call them more volatile things like water and methane, ices can form when you get far enough away from a young star. And this transition, so you can see here in this image, there's a bright young star in the middle, and there's a lot of hot material around the inner solar system. But then you finally get far enough away that things start to condense. And we call this the snow line, almost like you're looking up a mountain and you can see where it begins to snow, what altitude, how far away from the star can you get ices? And once you have ices, you have a lot of stuff to make planets out of. So, the rocky small planets in the inner solar system might not have been the best places originally to have those wonderful, watery, carbony compounds to start life going. This is an actual image from ALMA. ALMA is the Atacama Large Millimeter Array Telescope up in Chile, which I've had the privilege to go to several times. It's a beautiful, beautiful place. ALMA sees in microwaves and short radio waves, and it's able to take pictures of the warm gas around these young stars. And this is actually something that we can prove. I mean, we can actually see here's a young star system forming, and you can see they've superimposed where the orbits of Pluto and Neptune would be. And we don't see a whole lot of material, a whole lot of ices, a whole lot of water compounds any closer than that. And then when you get farther out of where the orbit of Pluto is, things cool off, and all of a sudden you get all of this stuff. And you see that the snow line is where we sort of see things begin to condense. So one of the first things that has to happen is you need to have a solar system that can mix itself around. What could do that? I don't know. I think a lot of you are as old as I am. I'm in my early 50s. And I remember the 1980s sci-fi show V, where there were aliens that had come to steal our liquid water. This whole idea that liquid water is really precious and really rare. Well, it is on the surface of planets. It is actually, I mean, we only know of one planet where you have stable liquid water on the surface. That's here. But liquid water itself is actually far more common in the outer solar system. And this is a lovely diagram that shows you if you could take all the liquid water on each of these bodies and put it in one big blob, how big would that be? And we're so proud of our water planet Earth, but we only have a little scrum of water, little film of water. We're a rock planet with a little bit of water on the surface. And both Europa and Titan, Europa around Jupiter probably has twice the amount of liquid water we do under its ice. And Titan, interestingly enough, we think has maybe as much as 4 times the liquid water that Earth has underneath its layers of methane rain and methane lakes. So liquid water is far more common in the outer solar system. Well, recently, and I think that I don't know how much you know. If you've read things like Astronomy Magazine or Sky and Telescope, you've heard about something called the Grand Tack hypothesis. And the word tack is used just like the sailing term, tacking against the wind. You can sail a sailboat into the wind if you tack the sail at certain angles, change the angle of the sail, and you can get your vector going forward. In this case, the Grand Tack hypothesis, which came about, I guess maybe about 15 years ago, began to suggest that the planets as they formed interacted with this heavy disk of material, all the dust and gas around the sun that was forming planets. As larger planets were forming in that dust disk, they were plowing through all of this dust. And that had the ability to actually slow them down. I mean, really, just literally the gravitational drag on these planets was slowing them down and causing them to move closer into the sun. And we now believe that Jupiter may have come in about as far as the orbit of Mars. So, Jupiter may have formed farther out, but then it actually came in through its interaction with this disk. And then the tack against the wind sort of comes from as other large planets started to form outside of Jupiter. There was basically gravitational tugging between those outer planets that tugged Jupiter back out little by little by little. And I mean, it's an amazing idea, but we actually see this happening in other solar systems, we believe. And there's increasing evidence that happened here. So, what happens if you have these giant planets kind of shifting orbits around? Well, you basically end up wreaking havoc. And what that is in the end is kind of good for the inner solar system. This is an animated GIF or a GIF, I don't know which one, but what you're going to see, and I'll play this a couple times, is you're going to see the orbits of the outer planets. So it'll start with Jupiter, Saturn, interestingly enough, Neptune, and then Uranus. And these are all of sort of the small icy bodies that formed outside the snow line, right outside the outer planets where ices could condense. You could have all this sort of icy carbon-rich stuff as well. As the orbits shift a little bit between these planets, the gravity of these giant planets moving around scatter all of these small icy bodies. So we actually do think there's evidence that Uranus and Neptune may have switched places. That Neptune was once farther in towards the sun than Uranus was. And that as Jupiter and Saturn jockeyed around with all of these little gravitational pushes, it pushed Neptune out, and that just everything came raining in. And this is probably how we got that era of heavy bombardment, where lots and lots of material came flying into the inner solar system, formed all the craters on the moon, and probably delivered much of the water, probably not all, but much of the water that we have on Earth today. So is it possible that, having something that can keep the planet stable, but not too stable? We now think that we may be like the second generation of planets. There were other planets before, but gravitational interactions between lots of planets trying to form disrupted everything. There were some planets that probably got thrown into the sun. There were some planets that probably got thrown way out into the outer solar system. And that's a possibility for this planet 9, planet X, that we might be sensing in some of the orbits of the outer bodies. But this of course is a beautiful picture from the Rosetta mission of the comet 67P. It's about 8 kilometers across, a dumbbell-shaped object. And we were able to land on this and sample the water and the organic molecules that were present on it. It's one of the places where, one of many places now where we find things like amino acids. So, the building blocks of our proteins, are very easily delivered in these objects. And we have some great missions coming up to sort of talk about and search for this habitability. I was really honored to be part of the OSIRIS-REx landing, which we landed on a comet Bennu. An asteroid Bennu, and we've taken, we believe, a few kilograms of sample that are now on their way back to Earth. They'll get here next year. And this is an artist conception of the mission we just launched called Lucy. And Lucy is going out to asteroids that have been trapped in Jupiter's gravitational orbit. I mean, they're basically at the Lagrange points in Jupiter's orbit. And we believe that these may be very, very ancient asteroids that come from the formation time itself, and they haven't been modified much in 4.5 billion years. And so, in fact, the name Lucy for the telescope is not an acronym, which is rare for NASA. It actually refers to the Lucy skeleton, the skeleton of that primate that existed about 2 million years ago. So we're looking for fossils. We're looking for our ancestors in these very early type asteroids that are out around Jupiter. Okay. Oh, hello. Oh, there we go. So now that we have water and organic molecules kind of flying around the solar system, there were 3 planets originally that were all in what we traditionally call the habitable zone. And the habitable zone, of course, is the distance away from a star that you are, where the temperature is about right, that you could have an Earth-like planet, perhaps liquid water on the surface if the conditions are right. Now, of course, we know that there are habitable zones out by the outer planets in the case of the moons. Things like Enceladus and Europa and Titan may have life on them, but in that case, they're warmed by gravitational interaction between the moons and the planets in the system. But these guys are kind of simple. I mean, they're basically just far enough away from the sun that they're about the right temperature. And these are depictions of the actual size, the relative sizes of these planets. So Venus is very similar to the Earth in terms of size and composition. Mars, a lot of people are surprised to know that Mars is only 1/10 the mass of the Earth. So it's a smaller planet, but it's actually a much less dense planet as well. So the amount of gravity available to hold down things like an atmosphere, that becomes a very important consideration for habitability. We now wonder if Venus might have been the first planet that was habitable in the sense it could have had liquid water. And the reason we're wondering that is we now know that stars naturally, over many hundreds of millions of years, become brighter as they age. They become brighter and a little bit hotter. So we're very quick to mention that this has nothing to do with current climate change trends. These are things that happen over 1 billion years. But Venus was probably the closer into the sun when the sun was cooler and dimmer than it is now. And so Venus might have had the right conditions for life before the Earth did. And that's a really interesting consideration that we're looking at. So let's start with kind of the classic place we've looked for life before, and that's Mars. So we now know, mainly from the rovers we've had all over the surface of Mars now. Well, I mean, in many different locations. I wish we could explore the whole surface. But we now know that Mars had standing liquid water for quite a long time. And, we don't know exactly how long and exactly when it went dry. I mean, now it's a very dry, very cold desert. And we certainly do see signs of there being some groundwater. There's definitely ice, as large ice caps that grow and shrink with the seasons. But liquid water on Mars is, it's not going to happen anymore, specifically because of the atmosphere. There's so little atmosphere on Mars that any liquid water would boil off. It has about 1% the atmospheric pressure of Earth. So Mars was habitable. It had liquid water. It had a thick atmosphere. It was warm. It had rain and snow. And it has organic molecules on it. I mean, the last couple of missions all detected organic molecules on Mars. So something happened that really, destroyed the habitability of this planet. And here's where we sort of think about how planets can maintain whether they're habitable. Now, for Mars, I just want to mention that there was a discovery that we did publicize about a month ago. And I think, it did get some press, but it's one of these things that I really wish got even more attention. This is a picture of the Mars Curiosity rover, which has been on Mars now for close to 10 years. And I love this picture because when we launched it, it was so clean and white and there weren't holes in the tires. And here's what it looks like, recently it's all dusty and the Martian terrain's been very hard on the tires. But about a month ago, we discovered as it was drilling through some strata, some layers of the rock on Mars, we discovered something that had it been on Earth, we would have said that's definitely from life. And that's always interesting when your Mars scientists that you work with sort of go back into their offices to try to figure out what it could be besides life. And that's what we had to do here. What it discovered is one of the earliest signs of life on Earth. And we're talking about 4 billion years ago. When did life first arise on Earth? Our biology is very good, interesting enough, at limiting the amount of organic molecules. The amount of organic molecules that come out of those beautiful clouds, there's those wonderful interstellar clouds. There are far more organic molecules falling out of the sky in meteorites and stuff than our body uses. Life selects small amounts of molecules to make building blocks out of. And amazingly, a typical carbon-rich meteorite has more different compounds than my body does by a lot, by like a factor of 10. And so when you drill down into these strata, a lot of times what you're looking for is an area where fewer molecules and fewer things turn up. And specifically, there are, for those of you that know a little science, there are different, what we call isotopes of carbon, which basically means an extra neutron. So carbon, normally has 12 protons, and it can have 12 neutrons, and sometimes it has 13 neutrons. And that makes the carbon-13 is a little bit heavier, just a little bit, but that means it doesn't react chemically quite as easily as the carbon-12. And so life always grabs carbon-12 and leaves the carbon-13 behind. And so one of the first things that we notice in the presence of life is we notice an imbalance between these isotopes. Something has basically just grabbed the carbon-12s and rejected all the carbon-13s. And we now have evidence of that in the strata on Mars. So there are some rocks that have been processed preferentially for what we think of on Earth as a definite life signal. And we don't know how you get that without life. The main thing that we can say is that we don't understand Mars perfectly. We don't understand, it has a very carbon dioxide rich atmosphere. Maybe that had something to do with it. And seriously, one of the explanations is that as the Earth was going around the galaxy with the sun, we flew through a molecular cloud that had more carbon-12. But honestly, the best explanation we know for that is that it was life. And we need to follow up to prove that that's true. But it could be that we have evidence of at least ancient life in the chemistry of the Mars rocks now. This is actually where the strata was taken. It's on the edge of Gale Crater, which was once an ancient lake bed. And those layers that you see are indeed from different layers of sediment in the lake being laid down. Wind, of course, has eroded it. And the thing that I really love is this is actually called Vera Rubin Ridge. And Vera Rubin was one of my mentors when I was in college. She's since passed away, but she was an amazing woman astronomer. She did a lot of work at Mount Wilson, but I worked at Mount Wilson as well. And I remember she said that they wouldn't let her up there. This was back in the early 1960s because they told her there weren't any women's restrooms. And these days we all use each other's restrooms just fine. So, but anyway, we could be looking at rock there that has evidence of ancient microbial life. And there, by the way, there's the little bore holes. I mean, that's what we do. So we have this wonderful instrument that bores small holes, only about 8 centimeters deep, into the rock, and then takes that and puts it into an oven and chemically analyzes it. And that's what we got the signal from. Okay, so now we got to start doing this in more places on Mars and searching for life, all over. The Mars Perseverance rover, which landed almost a year ago today, maybe it was a year ago yesterday. It was just about a year ago. It was an amazing, dramatic landing because we landed on this delta of a river that was much rougher than we had ever attempted landing on before, and we had to rely on the lander having a decent amount of AI, artificial intelligence. It had to be able to say where it wanted to land and where it didn't. And in fact, where it sort of randomly was coming down as it parachuted down, if it hadn't been able to divert, it would have ended up in a sea of sand dunes and probably not gotten very far. So it actually diverted from a terrain that it didn't like, and it landed on a different terrain, which is great. But as you can see here, there used to be a river channel. This was a water river. This is the wall of the crater. The crater is about 60 miles across. And here is where, just like in Louisiana, a river is draining into a deeper body, just like the Mississippi drains into the ocean, and it deposits all this material in what we call a river delta. And we wanted to be right there to see what kind of gook was coming out of that river. So that's where we landed. Here's an artist's conception of what that crater would have looked like, perhaps 1 billion years ago, perhaps 2 billion years ago. And we don't really know. But the neat thing is that this crater is the oldest lake bed that we've ever been able to explore anywhere, because there's no lake bed on Earth that's 1 billion years old. The continents have moved around, mountains have come up, all of that. So, I mean, this is sort of a lake bed. This lake was around when life was just getting hold anywhere in the solar system, maybe on Mars too. And I have to show this because I just love this. It's not too long. This was the first mission we had video cameras on different parts of the spacecraft. So you can see the wonderful rocket-propelled spacecraft that is lowering the lander down, and the lander's going down on this thing called a sky crane. The first time I heard about this, I worked at JPL. I thought they were nuts. They were like, yeah, we're going to have retro rockets. First, we're going to parachute. Then we're going to have these retro rockets. And to make sure the rockets don't stir up all the dust, we're going to lower it down on a crane. I was just like, you're nuts. But I mean, now it has worked twice. And I just love this real imagery. So let's just play that.
Altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane. About to conduct the sky crane
So there's
maneuver.
the views up and down, and here we go. There's the rover being lowered down and the view up.
About 20 meters off the surface.
We're getting signals from MRO. Tango Delta.
And there it goes. I love it.
Safely on the surface of Mars, ready to begin seeking the sands of past life.
And of course, it's COVID, so we can't do those fabulous NASA high fives. Everybody made fun of us on the internet during the Curiosity landings. We were high fiving, and we were so excited we were missing. So, long story about that. If you want to ask me in the questions afterward, I'll tell you about the high fives.
3 meters per second.
Okay, so and just kind of for fun, because I used to be a JPL person, when we actually saw the parachute being opened on one of these video cameras, we sort of looked at the parachute all over the country. Those of us that were staying up for this and said, what would they run on a fabric? I mean, why is that? What's with the pattern? What's with the red and white pattern there? And it took like 30 seconds for somebody to apply a digital code to it. And sure enough, it's a code. And it starts in the middle and kind of goes out from the center. So it's a digital code for the letters DARE, DARE, mighty things, and that's the motto of JPL. And then the very outer ring is the coordinates, the longitude and latitude of JPL. So gotta love those little Easter eggs. I know I do. And of course, these days we have satellites that are actually watching this continuously. We've got satellites that can see very, very high resolution imagery of the Martian surface. So the Mars Reconnaissance Orbiter actually snapped this real picture of the parachute opening. And then we even got a picture of the rover. So the little helicopter Ingenuity, as Ingenuity was flying away, we got a picture of the rover on the surface of Mars. So there we are with our car-sized laboratory on another planet, which I just love. Okay, now turning the discussion a little bit about what keeps a planet habitable. One of the things you need to remember is how we relate to the real thing in the solar system is the sun. And the sun actually is much more volatile and active than most people know. Space weather is becoming a big deal. In fact, NASA, we've got a whole big conference, that's what we're just putting together about space weather, partially because we lost 40 of those satellites that Elon Musk launched. He launched them into a solar storm. We knew about that. NASA told him about the solar storm. And a lot of people just can't seem to understand that the solar system really does change a lot. And there was so much stuff being ejected from the sun, very, very hot hydrogen atoms, electrons, all kinds of stuff, that it put a drag on the satellites and they were not able to reach orbit. And this is a picture of, just to show you kind of how dramatic this can be. This is an image that we took in 2012. It's a video. I don't know if you remember 2012, but that was the year a lot of people thought there was going to be a Mayan apocalypse. And so it was something to do with space, and they were calling NASA and they were saying, what's going to happen in 2012? And then we kept saying nothing. There's nothing going on. There's no alignments. There's nothing happening. Well, in July of 2012, we caught this very active region on the sun's surface. And this is taken through a filter that really, the only way something can be seen brightly.
Pool.
Sorry?
The owner.
Oh, maybe you have an open mic.
It's okay. Hold on. No. Don't walk away. I have the camera off. Okay. Do you think
I got an open mic? Okay. Anyway, this region here, it's bright because it's actually shining in millions of degrees. It's a very, very active, violent region of the sun. Of course, remember, you can fit 1 million Earths inside the sun. So it's a big, big place. And over the course of a couple of weeks, we were watching it become even more violent. It was starting to throw off stuff. Some region of the sun was getting very active, and you can actually see that our spacecraft view gets full of particles. That's the detector being kind of made crazy by the stuff hitting it. So this was kind of a dangerous region. It seemed to be throwing off a lot of material. And luckily for us these days, we have satellites all around the solar system. And we actually have satellites that are sort of on the other side of the sun from us. And this was taken by the stereo satellites, which in this case, they were kind of out by where Mars, in the direction about where Mars was. And you can see the image of the sun, and you see that this active region is actually kind of facing where the satellite was looking. You see that these streaming kind of white areas of the sun, that's the solar wind, a wind of high energy particles that fills our solar system. And sometimes it's very gentle, and sometimes it comes out in bursts. And when you get a lot of it, we get the auroras and stuff. I mean, it's a wonderful thing to see. But every once in a while, you get something even bigger than that. And so this is what happened on July 22nd, 2012. So you can see the solar wind is flowing away. We've got some active spots. There's a little hiccup. The sun throws off a few trillion tons of material. And then it goes kablooey. And you can see this stuff hitting our satellite. Basically, we had to reboot the satellite. So that was a major event. The sun threw out trillions and trillions of tons of high energy particles. And this was, we call it a coronal mass ejection, but this was a huge one. And if it had happened to go off in the direction of Earth, it would have probably brought down all of our power grid. We would have been in a global blackout. A similar event was captured by astronomers in 1859. It was called the Carrington event. And in 1859, luckily there was not a whole lot of electronics around back then, but they had telegraph wires. And telegraph wires spontaneously caught on fire. There was so much electrical current going through the Earth's atmosphere and our own magnetic field, that it was actually frying things in 1859. And this was a similarly powerful outburst. So the solar wind really can affect things. And in the case of the Earth, something that, again, habitability, one of the major things that makes a planet habitable, we now think, is the presence of a magnetic field. And this is an animation of one of these bursts of material coming from the sun. And the tracks of the particles all seem to be flying around the Earth. And that's because charged particles will follow a magnetic field. And the Earth has a strong natural magnetic field generated by our liquid metal outer core. The outer core has liquid metal churning and convecting around. And all of that moving metal generates a big, strong magnetic field. And luckily for us, that protects us from pretty much all of the solar wind. Like I mentioned, some of it gets in as the auroras. If you have a really big event, it can go all the way to the surface, but that's rare. And so that's a sort of an unsung major part of habitability is a magnetic field. So the problem with Mars was twofold. For one thing, Mars is small, and it didn't have the gravity to hold on to the gases of an atmosphere as well as something like the Earth or Venus does. Or Jupiter, for example. The reason Jupiter can hold on to a giant atmosphere is because it's very, very massive. Mars certainly had the ability to create an atmosphere. It had giant volcanoes, right? So these are the giant Tharsis volcanoes, with the biggest one being Olympus Mons. Olympus Mons is nearly 60,000 feet high. So I love it. You're flying in an airplane at 30,000 feet, you're only halfway up. And these volcanoes once produced huge amounts of gas, water vapor, carbon dioxide, methane. And the problem is the planet couldn't hold on to it. And also because the planet was smaller, its internal heat leaked away too. And so that wonderful, internal magma, we believe Mars once had a magnetic field as well. There's evidence in the rocks, the iron parts of the rocks are all lined up, that at one point it had an active core and a magnetic field, but it was just too small. It couldn't keep it going. And so it gradually froze up inside, and then the gases just escaped over time due to the solar wind. And this is still going on. Mars is actually still losing, many, many dozens of tons of atmosphere a day due to the solar wind. Okay, now then we go sort of the other side of the equation. Venus, again, we think was a habitable planet once. And this is an image from the Japanese mission that flew by, I think about 2 years ago, the cloud tops of Venus. Venus does have the mass to hold on to an atmosphere, so that's good. And there would have been a time where it had water vapor, the time where it had everything that it needed for life. But the problem with Venus, and then we don't understand why, but Venus does not have a global magnetic field. Very, very, very small magnetic field. And so what happens is that even with a planet that has a lot of gravity, you get some water vapor that is warmed up and it's in the outer layers of the atmosphere. And without a magnetic field, that water vapor is very prone to getting hit by high energy particles from the solar wind. And it breaks water up into oxygen and hydrogen. The lighter stuff, hydrogen, just flows right off into space, and the heavier stuff sinks down to form carbon dioxide. And so basically the solar wind stripped away the water from Venus's atmosphere over billions of years. And it left behind lots and lots of carbon and oxygen to form carbon dioxide. And then it left also behind this kind of witch's brew of heavy stuff. The clouds are actually made of sulfuric acid. So Venus lost the ability to have water. And water is so good. When it rains, it clears carbon dioxide out of the atmosphere. The temperature then got so hot under this thick carbon dioxide blanket that it baked all of the gases out of the rocks. So, Venus became this hellish thing where now it's 900 degrees on the surface. And the air pressure is similar to being a mile under the ocean. So, that's amazing. It's very dry. There's no liquid on the surface, but the air pressure itself is the equivalent of being a mile under the ocean. So why doesn't Venus have a magnetic field? Well, one of the weird things about Venus is it barely spins on its axis at all. The Earth spins once every 24 hours. Venus actually spins once every 5,832 hours. In fact, it takes longer for Venus to do one spin on its axis than it does for Venus to go once around the sun. The day is longer than the year. Is it possible that somehow a planet needs to have a spin to keep things alive and moving around in there? Maybe. These are taken from the Venera spacecraft that the Soviet Union sent to Venus, and we see a very hot, volcanic, dry desert. The rocks would be colored gray, but here they've colored them as you would see them as the sun is being filtered down through the sulfuric acid clouds. It'd be kind of yellow colored. And so we have been able to take brief images, but pretty much all the Veneras took an image or two and then fried. And they knew that. They understood that would happen. But it's amazing they even tried to do that. Venus is mysterious as well because it may be that the entire planet has very different ways of shedding heat than the Earth does. This is a radar image of Venus taken by the Magellan spacecraft. And the Magellan spacecraft was bouncing radio waves down to the surface. So it's a radar image, not a visible light image. And with radar, brighter areas will be smoother rock. Smooth rock reflects the radar really well. And if the rock is kind of uneven and gravelly, the radio waves will get scattered, so they won't look so bright. So basically, the dark and bright areas here show you smooth rock versus very, very jumbly rock. And you'll notice that there are these giant sort of loops and flows that seem to be associated possibly with volcanoes on Venus coming out of these craters, these calderas. And these lava flows seem to go all the way across the planet. And there aren't a whole lot of craters that look like they were, from meteorites. And I mean, Venus got rained on every bit as much as the Earth did by comets and asteroids. So now we're wondering if Venus actually may kind of like all go super volcano. The whole surface may just become a big boiling surface of lava every now and then. And that's a very different way for a planet to act. But when you look at the surface of Venus more closely, you see these really weird features that look like basically crushed souffles. These are sometimes 20 miles across. Looks like a giant bubble of magma came up, cracked the surface, and then sunk back down as it cooled. And is it possible the whole surface gets rid of the heat from the interior of the planet by just becoming a supervolcano? Right now, we don't know of any active volcanism on Venus, but could it be that the heat builds up inside, and then boom, and then it calms down again? Is it a very different way of having a planet? This is another radar image of those weird cracked magma features that we see all over the planet Venus. Venus does have one large mountain. The problem is we have no idea how you make a mountain that large. It's about 38,000 feet high, Maxwell Mountain. And Maxwell Mountain is high enough in altitude that it's quite a bit cooler than the surface. And so things condense out of the Venusian atmosphere and create snow right here on the summit of Maxwell Mountain. The snow, of course, there's no water. The snow is made of lead and bismuth. So it actually rains lead and metal. That's not a very nice place. A very interesting thing, though, happened. I mean, it seems like Venus would not be a good place to look for life at all. But remember, we said it might have been the first habitable planet. And this is me back at that ALMA place, that series of microwave and radio dishes at it's actually very close to 17,000 feet, the highest I've ever been. And they actually have this incredible detection coming from the atmosphere of Venus that we've known about for decades. I remember when I was in graduate school, a friend of mine who was a planetary specialist telling me about this, but they weren't really sure what this particular chemical signal from Venus's atmosphere was. And ALMA was able to pin it down very, very well. And it turns out to be a molecule called phosphine. And on Earth, the only way you can make phosphine is through biological processing. The only thing that makes phosphine is life, at least here. And interestingly enough, bacteria in the high altitudes of our atmosphere make phosphine. So bacteria exist everywhere on Earth. They exist, 3 miles down in a gold mine. They exist in Antarctica. And interestingly enough, they exist up in the atmosphere. We don't really understand the mechanism for getting bacteria up there, but it's up there. And amazingly, if Venus's surface is 1,000 degrees and really, really dense, air, go a little higher up to an altitude of about 60 miles, things get very temperate. It's almost like there's like water in the atmosphere. I mean, it's not the actual chemical of water, but it's sort of that density. So it may be that life did start on Venus and bacteria got everywhere just like on Earth. The surface died, but the stuff that was higher up in the cooler atmosphere may have survived. So we're on it. We're sending off our spacecraft. We just got approved this year for a dual mission to Venus. It will be the Veritas mission, which is on the left, which will be doing radar measurements and trying to find active volcanoes, looking for any changes on the Venus surface. And then the Da Vinci mission, which is a lander. It will go through the atmosphere with a parachute. It has a special instrument designed to detect the phosphine and see if there's any way we can tell that it's from life. And then it will actually go down to the bottom. We don't need landing gear because the atmosphere is so thick. It's like going through soup. I mean, worse than that. But that's being built right now. And this is something that I think is really pretty amazing. So this is an image of Venus that was just taken a couple of weeks ago by our Parker Solar Probe. Now, the Parker Solar Probe is studying the solar wind. It's orbiting the sun, getting a little closer all the time. And it's using the planet Venus in an interesting way. I'll talk about that in a second. But the amazing thing is we actually were able to see through the clouds of Venus, something we didn't think was possible. And this is invisible light. Sorry. I've been talking all day. I did a bunch of interviews today too. In this kind of fuzzy visible light image, there's an area that looks dark here that corresponds exactly in a radar image to something called Aphrodite Terra. Aphrodite Terra would be a continent on Earth. It's a part of the Venus surface that sticks up. It would have been like on a big continental plate. And Venus's atmosphere actually keeps heat, sort of continuously flowing around the whole planet. This is from the night side of Venus, but it's still hot because of that very thick atmosphere. And it turns out that the rocks are actually glowing faintly red. They're actually red hot, 800-degree rocks. And Aphrodite Terra is a little bit higher in elevation, so it's a little bit cooler. So it's a little darker. I thought that was wonderful. I mean, we're actually looking through the clouds of Venus, and we can see the continents, and they're glowing red at night. All right, so let me just play this little video, which I think is kind of fun. Okay, so why are we flying by Venus all the time if we're actually trying to observe the sun? And I know that all of you out there really understand what an orbit is, but a lot of people don't. A lot of people don't understand that when we orbit the sun, we are freely falling towards the sun at all time. But the Earth has so much velocity, velocity left over when the solar system formed, spinning around the sun, that even as we fall towards the sun, we keep missing it. And that's what an orbit is. The astronauts are not weightless because they're far away from Earth. In fact, if you were just at the altitude that they are, about 200 miles above the surface of the Earth, you'd still be about 90% of your weight. They're weightless because they're falling. They're in orbit. They're continuously falling towards Earth, but they're going fast enough that they always miss it. And so when you understand that that's really how an orbit works, the interesting thing is it's very difficult to go to the sun. So let me play that little video.
NASA's Parker Solar Probe will soon fly closer to the sun than any spacecraft before it, about 4 million miles from the visible surface. But getting that close to the sun requires some fancy orbital mechanics. It takes 55 times more energy to go to the sun than it does to go to Mars. Why is it so hard to get to the sun? The answer is related to why Earth doesn't just fall straight into the sun, despite the strong gravitational attraction. Earth, and everything on it, is traveling very fast, about 67,000 miles per hour, in a direction that is basically always sideways relative to the sun. If you launch a rocket from Earth straight toward the sun, it won't lose that sideways speed, and so it will miss the sun. The only way to get the rocket to go right into the sun is to cancel all that sideways motion. Leave even a little bit, and it will miss the sun and enter a new orbit. To cancel Earth's motion, you have to launch the spacecraft backward as fast as Earth is hurtling forward. But 67,000 miles an hour is really fast. Spacecraft have to go upward at only 25,000 miles an hour to escape Earth. Getting to Mars only requires a bit more speed, 29,000 miles an hour. New Horizons, which NASA sent rushing out to Pluto, managed 36,000 miles per hour, or a little more than half what it would have to do to hit the sun instead. Since Parker Solar Probe plans to fly past the sun, it doesn't need to cancel out all of Earth's sideways speed, but it does need to remove 53,000 miles per hour of it. That's why it's using one of the most powerful rockets available and additional gravity assists from Venus over a period of several years. In this case, rather than speeding up the spacecraft, as in a typical gravity assist, Venus slows down its sideways motion, so the spacecraft can get close to the sun. When it finally does make its closest approach to the sun, Parker Solar Probe will have lost much of its sideways speed, but gained a great deal of overall speed thanks to the sun's gravity. Parker Solar Probe will hurtle past the sun at 430,000 miles an hour, the very first human-made object to get that close.
And you heard that right. 430,000 miles an hour is how fast it's going when it gets close to the sun. So I love it. I mean,
NASA's Parker.
I love the fact that instead of using something like Jupiter or Saturn to slingshot us out, to actually give us energy to go out into the outer solar system, we're using Venus to slow us down. We're going the opposite way around Venus. So that's really kind of a neat way of using a gravitational slingshot. So I mean, kind of wrapping this up, it now looks like maybe even a wonderful system of plate tectonics really, really helps the habitability of planets. Our planet is able to shed heat from the interior in a very gentle way, if you consider earthquakes and stuff gentle, but these plate boundaries allow plates to slide under each other, to melt, to replenish rocks. New gases are released underground that come up through the volcanoes. So our planet seems to be wonderful at kind of regulating itself. But the neat thing to remember is that life on Earth was pretty much just microbial life for the first 2 billion years of life. Not much happened. We basically were blue-green algae, for billions of years. And then something happened that actually set evolution in a really, it really kind of gave it a smack to get it going. All of the blue-green algae and all of the plankton and all of the bacteria on the planet, it was photosynthesizing. And so photosynthesis, breathes in carbon dioxide, it uses carbon dioxide, and the waste gas is oxygen. So, I mean, the release of the first oxygen into the Earth's atmosphere was largely because of that bacterial microbial life. But the neat thing was this life was very successful. The microbes spread all over the surface of the Earth until finally there were so many photosynthesizing microbes. They were breathing in so much carbon dioxide, they broke down our natural greenhouse layer. They sucked so much carbon dioxide out that the planet froze. And something that's changed since I was in college is that we now know that the Earth almost froze all the water twice. It went through 2 what we call snowball phases. We have evidence of glaciation all the way down to the equator during this time. And incredibly, the Earth would have looked something like this. We would have been, there probably would have been a little bit of open water around the equator, but we would have resembled Europa much more than we resemble the Earth today. And we froze in these snowball phases for more than 10 million years each. And what eventually started things going again was volcanoes. Volcanoes bringing more carbon dioxide, more methane, more greenhouse gases into the atmosphere and getting us out of these massive ice ages. This happened about 1 billion years ago. And this was also the time where life starts to get more and more complex very rapidly. So we think that this stress on life, all these microbes you probably killed most of them. The ones that survived were crushed together probably in little bits of water inside ice. There was sort of this smack that actually made life change. So maybe to have a habitable planet, you need a stable planet, but not too stable. This is actually an illustration from one of our supercomputers. Of course, the continents were in different places back then, 1 billion years ago. But it shows you where we have, where we think the open water might have been, and everything else was pretty much frozen. So incredible to think that the planet once looked that differently. And remember, that had to do with life. Life has been deeply affecting the climate of the planet ever since life started. So I guess I'll leave you on this one. We now know of systems. This is an illustration of the system TRAPPIST-1. These are actual this is obviously an illustration, but we have actual observations of 7 Earth-sized planets going around this star. This star is very dim. It's a red dwarf, a very small star. And this was actually the real data you can see here. That there's a general light level that the star is shining. And every time one of these planets moves in front, you get a drop in the light level. And these 7 planets, talk about, for those of you that like math, fun with Fourier transforms, not only do you have 7 different orbits going around the little star, but these planets are so close to each other. They actually tug and pull on each other gravitationally so much that they change each other's orbits up to about 30 seconds each time they go around. It's incredible. I would never have believed a system like this would have existed, but there it was, in the observations. This system is so small that these 7 planets are all in about the diameter of the Galilean satellites of Jupiter, about twice that. So if you think about, the big moons around Jupiter after Callisto, about twice that distance, 7 Earth-sized planets around this little star. And, could any of these be habitable? Well, they're about the right distance for the temperature to be right for liquid water. They are probably all tidally locked, like the moon. They're so close to their star, only one side faces that star all the time. But we've been doing supercomputer models that with an atmosphere and with oceans, that he could be distributed enough to actually have a more moderate climate around the whole little world. And so now what we're doing is we're finally kind of looping back to the beginning here, getting ready for the James Webb Space Telescope to observe this system and others. And James Webb will have the power to see what the atmospheres are like. It will have the observing and resolving power, not to see unfortunately, the little disks. They're still too small for that. But it'll be able to take spectroscopy of the atmospheres. And we will know. We'll know whether there's water vapor. We'll know whether there's methane, carbon dioxide, ozone. Ozone is a very easy signal for the fact that there's lots of oxygen. And it really could be that if you have me back in a year's time, I'll be able to report on planets we now know have an Earth-like atmosphere. So we're getting closer to understanding what makes a planet habitable. And now with James Webb, we're finally getting to the place where we can even observe that. So stay tuned, both in our solar system and in solar systems beyond. And with that, I will end the show. I'm happy to take questions.
Wow, that was amazing.
I have a question.
Sure.
You mentioned in 2005 there was a neutron star
Yeah.
that blew off quite a bit of the atmosphere.
Yeah.
Does that have a name, and where is it located?
Yeah. I have all that. Yeah, I don't know it offhand. I don't think the neutron star has a name. I think it has just a telephone number. But if you do, I mean, this is all documented because it really, we had high energy satellites up at the time that actually observed this, and we also observed it. Basically, the Earth's magnetic field rang like a bell afterwards. And so let me just make sure I have I'm just calling up a Google window here. Neutron star blows off Earth atmosphere. Yeah, okay, so it was, here it is, cosmic blast, magnetar explosion rocked Earth on, hold on a sec. 2004, I'm sorry, it was December 27th, 2004. I'm only 3 days off. So 8 years ago, so this was written before. So this is something that you can find just on Google.
Okay.
And so the flood of gamma rays and X-rays was observed by the RESI satellite, the Integral satellite, and the SWIFT satellite. And yeah, so the name of it is SGR 1806-20. And yeah, it's about 50,000 light years away, and it probably says somewhere what constellation it's in. But yeah, so just do a Google search on a neutron star that blew off Earth's atmosphere.
Well, now that I have the date,
yeah,
that'll put me pretty much in the ballpark.
December 27th, 2004.
Thank you.
1806 minus 20, that would be like Sagittarius or Scorpius, somewhere in there.
Yeah, probably.
Wow.
Where SGR comes from.
You know, I mean, some people think that gamma ray bursts are the limiters to civilization. I mean, I hope not. But I mean, so we observe a gamma ray burst about once a day, and of course that's because our high energy satellites can see all of the galaxies in the sky. You know, all the ones in the visible universe, because these things are so bright. But you know, you see the ones that we see are only the ones that have the jets aimed toward us too. So there's plenty more that's going in directions we don't see. But they're fairly common, and yeah, I mean they are energetic enough. If one went off anywhere in the galaxy pointed at us, where it would rip the atmosphere off. I mean, we wouldn't even see it coming because the gamma rays come at the speed of light. So,
wow.
Yeah.
Well, let's hope that doesn't happen. Hey, great talk for starters. If I can ask you a question, you ended towards the end sort of talking about TRAPPIST, which is potentially planets like ours and things that we can look at. And I understand they're very close. So, but
Great.
We'd like planets like ours, maybe around G-type stars further out than those. Is there any prediction when we think our technology is going to be up for that? And
well, like I said,
finding those?
It's mainly a timing problem. Like I told you before, all we need to do is do this longer. Because, you know, I mean, we definitely do know of Earth-like planets in Earth-like orbits. We absolutely do. I mean, we just simply know a lot more of these very close-in stars because they're easier to find. So these planets that go around so quickly, you can confirm them really, really easily. But I'm not sure, because it's changing all the time. But I think we know of at least 10 planets that are Earth-sized in an Earth-like orbit around an Earth-like sun-like star. So there definitely are some, and absolutely, JWST will be looking at those as well. Yeah.
Cool. Thank you.
Lou, if you lived on one of those planets, you'd have a lot more birthdays.
That's for sure.
I need more birthdays, of course.
I don't need any more birthdays. You know, the thing that amazes me about those worlds is that they're so close to each other. I mean, they're much closer than, say, the moon is to us. And so you'd have 7 Earth-sized planets like up in the night sky at sunset. And I mean, it looked like something out of a sci-fi novel. I mean, you'd be able to see the surfaces of the planets, you know, the oceans and continents or the ice or whatever, you know, the lava, if it's one closer into the sun, you know, can you imagine that that's a real place? Wow.
And it's close, right? TRAPPIST is 12 light years, right?
Yeah, that's right. Yeah.
Yeah. Wow.
I mean, we're definitely going to observe Proxima Centauri b, right? So that's the nearest exoplanet to us. And Proxima Centauri b is an Earth-sized planet. It's a rocky planet. The problem is, and this goes back to our discussion, Proxima Centauri, Alpha Centauri Proxima, the nearest star to us, is another of these red dwarf stars. They put off huge solar flares. I mean, like, things that are many, many thousands of times more powerful than we observe from the sun. So this little planet is pretty close to it. And it might be about the right distance away to have the right temperature to be Earth-like. But, we think it's getting strafed by this huge solar flare. So, I mean, if it has a really strong magnetic field, maybe it can hang on to something. But there's no way we can tell. There's no measurement we can make at this point to say whether these planets have strong magnetic fields or not.
I have a question about the radar images of Venus.
Mm-hmm.
Do they come from a satellite or from Arecibo?
They come from a satellite. They come from the Magellan mission. So the Magellan mission was orbiting Venus when it took those. So it got very wonderful high resolution radar imagers. And I think the Magellan, they were in the 90s, I believe, the 1990s. All that data is available from NASA. So you can just, you can have as many Magellan images as you like. All of those wonderful, like fallen souffle features are just incredible to look at.
Cool.
I have a couple of questions. First question is, you say that carbon was a very common atom in the universe.
Mm-hmm.
And I guess we can have direct evidence probably from the clouds, dust that are close to us. But do we have evidence of that, for instance, in distant galaxies and further away, or do we just extrapolate this information?
Oh, no. I mean, so anything you can get a good spectrum of, you can see that there's carbon. And so, obviously, the clouds around us that are forming stars are very, very rich in carbon compounds. So, the Orion Nebula, things like that. I mean, so we can definitely see things in the nearby ones, but then you can also see the signal of carbon in the interstellar dust of galaxies like Andromeda, or farther away galaxies. I don't know what the farthest away galaxy we've seen carbon in, but because that's a pretty easy chemical fingerprint to see, my guess would be even billions of light years away. So yes, carbon is all over the place. It's a very easy atom to make when stars go through their normal lifetime and die. Yeah.
Thank you. And the second question is about Venus.
Mm-hmm.
So Venus still has an atmosphere.
Big one.
It's closer to the sun than us. And yet, how come the solar flares or solar winds haven't stripped it off like they've done, for instance, on Mars?
Well, so the thing about Venus is it has a higher gravity, right? So Mars is only 1/10 the mass of Venus and Earth. Venus and Earth are similar. They're very close to being the same mass. And so with Mars, it wasn't able to hold on to those gases against the solar wind pressure. Venus and Earth have enough gravity that they're pretty good at holding down the most of the stuff. But the problem with Venus, and we talked about this, was that all the lighter material got stripped away. So over billions of years, things like water vapor, there's basically no water vapor. Venus is very, very devoid of water. And, all the lighter stuff got stripped away, but the heavier stuff like sulfuric acid and carbon dioxide, that stayed around. So it was able to hold on because it has a higher gravity.
Thank you.
Mm-hmm.
Shell, I have a question about the JWST.
Yes.
So there's 4 instruments on that thing?
Oh, depending on how you count it, because they have different modes. But yeah, I think basically.
Do they share the same light cone or?
Yes, there's pickoffs. So I think that one of the things that's different about JWST as opposed to Hubble is that we can operate several different instruments at once. So there are pickoffs into that focus. So the secondary mirror has a focal point, and then there are light pickoffs to the different instruments. And I believe Webb can at least have 2 instruments working at the same time. So that's one of the reasons we can do science with a lot higher efficiency with Webb than we did with Hubble.
So you're saying there's 2 sensors that are taking up the space of the light cone at the same time, or are they swapping back and forth?
So the focal plane basically has pickoff mirrors that go to the different instruments.
Okay.
So I mean, there's a focal plane, but then mirrors can put some of the light in one, some of the light in another.
And I'm assuming, I guess, all of it, well, do all these work at once or do they take turns?
So as I was just saying, the thing that's different about Webb is that I do know that more than one instrument can work at a time. I don't know if all of them can work at a time, but I do know that they can use more than one instrument simultaneously. Yeah.
The reason why I ask is the bigger the sensor, the more resolution you're going to get, right?
Right. Yep. Mhm.
So, okay.
Yep.
So they split that is what you're saying.
Yeah. Like I said, there's pickoff mirrors. There on the web website, there are these lovely animations of the light paths through all the instruments. If you really want to get geeking out in the wonderful technical details, you can see the light paths through the whole thing. So they'll show you, here's where it gets picked off the main focal image, and then it goes to here, to here, to here. There's the spectroscope, there's the imager. So when we were doing our launch coverage, we had experts that had actually built the instruments, and they would sort of take us through how the design worked. So yeah, I do know that more than one instrument can work at the same time. I don't know if all of them can.
Thank you.
Hmm?
With the image that you showed of coming from James Webb with the starlight focus, does that mean you're on an accelerated path to get to the images?
Well, at the very least, it means everything's going well and quickly. I don't know whether they're ahead of where they hope they'd be through the whole commissioning. That's been the case. Things have gone so smoothly. We had built in some time. It's like, well, something's going to be a little wobbly. It'll take a little longer, but it hasn't. Everything's gone really well. So as of today, all mirrors are seeing starlight, and now we just do the very, very fine guidance deformations of the mirror, tilting this way and that to get it to a little pinprick and not a spread function. That's this is the stuff that my husband was really instrumental in that algorithm as to how you want to do these fine adjustments, and so that's something that I'm just watching with joy, if a bit of sorrow. He died before he could see this. Yeah.
Oh, how sad.
Yeah.
Well, do the mirrors do a separate collimation and then also focusing, or is it all one operation?
Everyone's separate collimation, separate focusing for each mirror. Yep.
Could you speak a little bit on why that particular star was chosen? I mean, for amateur astronomers, we always usually pointing to the North Star, for example. This one's pointing to a empty part of space in Ursa Major, I believe.
Well, to tell you the truth, I don't know what target was chosen to focus on and why. So that's something you have to ask our optical team. And okay. The main optical person that I work with is a guy called Lee Feinberg, and he and my husband Andrew work together a lot. So he's still around. Andrew wrote me a goodbye letter. He died of cancer, so we knew it was coming. But he wrote me this letter in Elvish that it's in Lord of the Rings Elvish. That it's my first tattoo. I had it tattooed all around my body, and so I brought that to the web journey with him, and we've been with him since I was 23. So I am adjusting to being a widow. But he would be so happy right now. He'd be so proud of his focusing algorithms working. Yeah.
You have every right to be proud.
We all go through grief in our life, and
yeah.
It's something that makes us human. Yeah.
Yeah.
But I have to say that this year, even though it's been a crappy year in many ways for me, the family of people working at NASA and being able to work on the James Webb launch, this was a major bright moment in my last year. It really helped to be working with these wonderful people on this fabulous mission, and then to have it all go right. Just so glad.
Is most of the science done out of JPL? I mean, I know like Hubble was done under the Space Telescope Science Institute, whereas most of the science done for JWST.
So we're also working out of the Space Telescope Science Institute. That will be the main science leader. So the way it will work is that we will begin with some early release observations, probably in May, of beautiful things. Some will be solar system objects, some will be objects in the sky. They were chosen specifically that the public would find them beautiful. And then we go into a period where astronomers all around the world have named objects they really would like good observations of, and that will be immediately public. the data will be public to anybody. After that, we go into a cycle very much like Hubble, where there will be yearly review panels that you will submit proposals to. And so the web, like Hubble, is a public observatory. Certainly the people that built the instruments and the director, they all have some amount of time dedicated, but the vast majority of time is open to any member of the public to apply. And there'll be a yearly, so that we've already chosen the first year of observations. They, even before it launched, I'm sure they were more than anybody else really hoping that worked. We've already chosen the first astronomers all over the world, who got high priority targets. And the thing that I have to report is we did this very deliberately. We did it double blind this time because we found that people who were more senior in their jobs and had names that were, very well recognized, even if we asked review committees to be impartial, they're like, oh, that's a wonderful person. I know them. I'll give them time. And so we did it all double blind this time. And we have a record number of women and people of color and different nationalities and early career scientists. So this time, the time just went to people that had the best proposals.
That will be very exciting. I hope you can report back on that when the time comes.
Yep. Yeah, we're gonna get started soon. Yeah.
Yeah.
In fact, the way that we did this is now being studied by all of NASA missions as to how to get data out. That we're still seeing biases in who gets proposals accepted, and so the idea of really making the data equity, we're calling it, making sure the people that have the highest reviewed scientific proposals get the data.
It's exciting.
Yeah. Well, hey, and you guys know where to find me. I'm not very far away. Maybe when we start having meetings again, I can come sometime. But it's certainly been a pleasure talking with you, and I'm happy to come back again.
That would be awesome. This
I
has been
hope you
amazing.
can.
Thank you.
Yes.
It's been great.
Thank you very
Thank you.
much.
I understand Lou has the web in his telescope. Is that right?
Yeah, I found it. It's
You
kind
want to share it?
You want to see it? Sure.
Yeah.
It's really boring. It's just like a point source. of
Not, yeah.
Well, hold on a minute. Let's see here.
That's a Sombrero Galaxy.
Okay. Well, that was a Hubble version.
Yeah.
Okay. You see the screen here?
Mhm.
I'm going to zoom in. It's really faint. So you'll have to look in this area here. Wait a minute. Let me get my little mouse pointer. Why is it not working? Nothing ever works when it needs to, right? All right. Well, I hope you guys can see that. Anyway, I'll have to manually move through, but there you can see there's a little light source moving across this way. There it is right there. I don't know if that's coming through or not, but I'll have to do it over and over again.
But that's our baby. There it is.
It's like a
Yeah.
17.1 magnitude or 17.5 or something. It's
Oh.
right at the edge of the envelope of what my telescope and camera can capture. So it does get brighter than this. I think it's gotten as bright as magnitude 13 or 14, but this is I'm surprised I even was able to find it. This was a pain because it's so small. But anyway, all right, that's it. A bunch of nerds looking at the JWST.
Hey, we're
call
so
it a nerd.
happy you are. That's right. Yeah.
Wow.
Thank you again, Michelle, on behalf of everybody here. We really enjoyed everything you had to say, and thank you for all you do.
Yes.
Oh, it's
so
an
much,
honor. Yeah.
so much energy, contributing to science the way you do, communicating it the way you do to wide audiences. We really appreciate it.
The
Thank you.
enthusiasm and excitement as well.
Well, as I said, it's an honor to represent NASA and the team. They are amazing. I mean, I get to work with what I think the best people in the world. So anyway, good night. Thanks for having me.
Good night.
Good night.
Good night. Thank you.
Thank you.
Good
Thank you
night.
again.
Thanks for coming. Thank you.
Thank you.
Another great speaker, Jeremy.
Yeah, it's amazing.
Excellent.
Oh, it's the first time I actually saw the JWST since I was looking at it tonight.
Life is good.
It's been hiding from me.
Jeremy, I had a question about the live stream as we go, hopefully back to Radnor. Do we have any equipment bought yet, or
No, I mean, I was hoping to just do a test with just computers and see how that works.
Okay, okay.
I guess we'll have to, our new
Yep.
form technical committee, now that we have
Yeah.
people.
What we need to do, Jeremy, is we need to schedule a meeting in the next week or two,
Yeah.
I think.
What about internet? Do we have access to the?
Well, that's one
That's
of the
gonna be
things
the
that we're
big
going to
thing.
do a speed test. We're going to go down and do a speed test. That's really the most important thing, and 5 megabits per second should be fine if we truly get it in the room, right? And then we could stream using a tool like OBS, which is free software on a laptop, or we can get a streaming bridge, which won't be very, very expensive. And then we have to decide ultimately how sophisticated and compelling we want it to be.
So there's no hardwired cable we can plug into?
There is not a cable unless we arrange for it specifically. And we've previously talked to the venue. I think everything is up for grabs again, but we'd previously talked to the venue about doing stuff and like renting the projector, for instance, and having the wired internet. And it was quite expensive. It was like $100 or more a meeting. So.
I think we're better off having our own equipment, because if we show up and something doesn't work, who are we going to find at 7 o'clock on a Friday night from the township to help out?
Yep.
No one.
Yeah, I totally agree.
Yeah, I definitely think it should be our equipment. But we should definitely get together and maybe get some we'll get some initial equipment and do some testing.
Well,
And kind of go from there.
Well, since everyone, of course, enjoys staying online while we're doing our business, do we want to just pick a date and I'll set up a meeting?
Sure.
So
next week is kind of crazy, but the
yeah,
week
no.
after that is going to be fine.
Yeah, how about Thursday the 3rd at 7 p.m.?
Thursday at 7. Okay.
Well, is this going to be to go to the Radnor building? Because we'll have to get permission from them.
I thought we would just do a remote meeting for starters.
Oh, just do a Zoom meeting. Oh, yeah, we could do that.
Yeah.
Getting to Radnor, I'm going to have to find out what their schedule is.
Yeah. So, Jeremy, could you set up a meeting for that actually yourself?
So Thursday, March 3rd. I mean, if you want to do something a little sooner, I could do a Zoom meeting sooner than that.
I'd be up for like the 24th.
All right, well, let's email and we'll sort it out. Well, I got to go through my calendar.
So since we're into the nitty gritty here, I guess we should say goodbye to all our YouTube visitors, and thank you very much for joining us.
We love our YouTube visitors. They shouldn't go. Bye, YouTube.
Bye all. Tune in next month.